Hello students, today we are going to discuss next concept in the chapter real numbers. The second concept in this chapter is the fundamental theorem of arithmetic. To understand what exactly is fundamental theorem of arithmetic, we will start with some concepts which are required to understand this theorem. The first one is factor. What is factor of a number? A positive integer is said to be factor of some other integer if it divides that integer completely. Means, for example, if we have a number 12, we can say that 3 is a factor of 12 because 3 divides 12 completely. Means it does not leave any remainder. That is, remainder is 0. To discuss this in more details, let us consider the following examples. If we consider the number 12, the divisors of 12 are 1 divides 12, 2 divides 12, 2 into 6, 3 into 4, 3 divides 12, 4 divides 12, 6 divides 12, 12 also divides itself. You always have to remember one thing, that 1 is the divisor of every positive integer, as well as every positive integer is the divisor of itself. Getting it? So here 1 as well as 12 are also the divisors of 12. Next example, 49. If we take 49, you can see that 1 divides 49. The next number which divides 49 is 7. 7 sevens are 49 and 49 itself. Third example, 17. There are only two positive integers which divide 17. That is 1 and 17 only. Fourth example, if we take 2, again there are only two positive integers, 1 and 2, which divides 2. Next example, fifth one, if we take 120, you can see there are many numbers which divides 120. The numbers which divides 120 are 1, 2, 3, 4, 5, 6, 8, 10, 12, 15, 20, 24, 30, 40, 60, 120. So all these numbers are called as factors of 120. Getting it? Similarly, let us take sixth example, that is 1. There is only one number which will divide 1, that is 1 itself. So 1 has only one factor. Getting it? So from above examples, we come to know that the integers which divide a particular number are called as factors of that number. Getting it? So this concept is required to us to discuss the next type of numbers. We are going to use this to segregate the numbers in two main formats. The first one is prime number. A positive integer having exactly two factors is called as a prime number. So from above 6 examples, we can say that 2 and 17 are the prime numbers because they have exactly two factors. Next one, we can see some examples of the prime numbers, that is 2, 3, 5, 7, 11, 13, 17. You know that all these numbers are having only two factors, that is 1 and that number itself. Next type of number which we are going to study is composite number. If a positive integer is having more than two factors, that is 3 or more than 3 factors, then it is called as a composite number. In above 6 examples, we can say that 12, 49 and 120 are composite numbers because they do have 3 or more than 3 factors. Let us discuss some examples of the composite numbers. 4, 6, 8, 9, 10, 12, 14, 16. All these are the examples of the composite numbers because they have more than two factors. If we come to discuss about 4, what are the divisors of 4 or factors of 4? 1, 2 and 4. So 4 has 3 factors. As it has 3 factors, it is a composite number. Getting it? Let us see some notes. 2 is the smallest prime number. Though 2 is even number, it is also a prime number. Remember that in fact 2 is the only even prime number as it has exactly two factors. Next note, 4 is the smallest composite number. if you are thinking that 2 may be the smallest composite integer, it's not like that. You can see in the list that 4 is the smallest composite number because 4 has 3 factors. Next one, the number 1 is neither prime nor a composite number. Why is it so? Because 1 has only one factor. To be a prime number, a positive integer should have exactly 2 factors, but 1 has only one factor. You can see in example 6. And to be a composite number, a positive integer should have 3 or more than 3 factors. This is also not satisfied by this number 1. So 1 is not satisfying the definition of a prime number as well as a composite number. That's why 1 is neither a prime nor a composite number. But one thing which we can say for sure is 1 is the divisor of every positive integer as well as every positive integer is a divisor of itself. So these two things you have to remember while studying the fundamental theorem of arithmetic. So this is the required part to understand what exactly is the fundamental theorem of arithmetic. So first of all, we have studied factor. Factors are nothing but divisors of a positive integer. Prime numbers, the numbers having exactly 2 factors, and composite numbers, the numbers having more than 2 factors. Getting it? Let us start with the next part of this chapter. To understand what exactly is the fundamental theorem of arithmetic, let us consider the following examples. Actually, fundamental theorem of arithmetic deals with prime factorization of the given numbers. Means if we have given a composite number, that composite number we are going to divide only by the prime numbers, and in the end we are going to show that every composite number can be written as a product of its prime factors. So first of all, ladder method which we are using to do the prime factorization of a composite number. Since in lower classes also you have studied this method, let us consider a couple of examples here. See, the first example, 2,52,525. If we are going to factorize this, clearly we can see that this number is divisible by 5. So first of all, we have divided by 5. Then dividing by 5, our quotient will come 50505. So once again that number is divisible by 5. We know the divisibility test of 5. So again dividing that number by 5, we will get another number, that is 10101. Now this number is not divisible by 5. Clearly we can see that. So what are we going to do there? Now addition of all the digits is coming 3, means this number should be divisible by 3. So let us divide that number by 3. Dividing 10,101 by 3, we will get 3,367. Now again this number is divisible by 7. So when we divide this by 7, we'll get quotient as 481. This 481 is divisible by 13. When we divide this by 13, our quotient will come 37. Now we are not going to do it further because 37 is now a prime number, so we cannot factorize this. So in this way we are going to do it. Already we have studied this method in the lower classes. So here we can say 25, that is 2,52,525 can be written as a multiplication of the prime factors 3 into 5 into 5 into 7 into 13. The same can be written as 3 multiplied by 5 square into 7 into 13. Now let us discuss the second example where we have given a number 3,63,636. First of all, we can see that this number is clearly divisible by 2. Remember that we are going to divide only by the prime numbers. So first we are dividing by 2. Dividing by 2 will get 18181. Once again it is divisible by 2. So we'll get quotient as 90909. Now this number is divisible by 3. So dividing by 3, we'll get quotient as 30303. Again this number is divisible by 3. Dividing by 3, we'll get 10101. Now this 10101 is again divisible by 3. So we'll get quotient as 3367. When again this 3367 is divisible by 7. So we'll get quotient as 481, and then 481 is divisible by 13, so we'll get 37. Remember that you start doing it from the in one sequence from the first prime number. You start with 2. If you are going to do prime factorization of the given number, you first of all start with 2. If the given number is divisible by 2, you divide it by 2 only, unless and until it becomes not divisible by 2. Then you start with 3, then next prime number is 5, then you go for 7, then you go for 11, then 13, and in this way. So it will be better to write it properly, and don't divide given composite number by some composite number like 4, 6, 8, 9. Don't divide by these numbers. We have to divide only by prime numbers. So here this number 3,63,636 can be written as 2 into 2 into 3 into 3 into 3 into 7 into 13. That is nothing but 2 square into 3 cube into 7 into 13. So in these two examples, we can see that both the numbers given to us are prime numbers, composite numbers, and these composite numbers we have written as a multiplication, or we can say product of the prime numbers. In both the examples, we can see that both the questions we have not used any composite number in the multiplication. So from these two, we come to know that every composite number can be written as a product of its prime factors only. Getting it? Now someone may change the order, but that order is not important. I told you start from 2, then go for 3, then 5, then 7, 11, like this you do, so that it will be better for you. And don't divide by any composite number. Let us take one more example. So this is the ladder method to do the prime factorization, which you have studied in the lower classes. There is one more method, actually it is same only, which is called as factor tree method, which is again quite similar to this one. Instead of using these lines, we are going to use something different. See, suppose we are going to do the factorization of 1092. So first of all, we'll start with 2 and we'll divide this number by 2. We'll get 546. Then actually we should divide by 2 again, because 546 is again divisible by 2. It doesn't matter the order. Then you can divide by 3, then 7, and in the end, when you will divide 91 by 7, you will get 91 as 7 into 13. Now you know that 7 as well as 13, both the numbers are prime, so we cannot do the factorization further. So that will be our last step, and the numbers which are encircled are nothing but the prime factors of 1092. So 1092 can be written as 2 into 2 into 3 into 7 into 13. Getting it? So once again, 1092 is a composite number, and this number you can see has been written only as a multiplication of its prime factors. So let us consider some more examples. If we take example of 120, and if we do prime factorization by using ladder method or factor tree method, doesn't matter which method you are going to use there. You can use any of these. You can go with ladder method, or you can go with factor tree also. So by doing the prime factorization, we will see that it will be like, it can be written like 2 into 2 into 2 into 3 into 5. That is nothing but the prime factorization of 120, which can be again written as in the power form as 2 cube into 3 raised to 1 into 5 raised to 1. Next, let us take one more example. 1000. If we do its prime factorization, we will get 2 into 2 into 2 into 5 into 5 into 5. Okay, so in power form, this prime factorization can be written as 2 cube into 5 cube. So this is the way. Now we will see what exactly is the statement of fundamental theorem of arithmetic. The statement for fundamental theorem of arithmetic is given as follows. Every composite number can be expressed as a product of its prime factors apart from the order in which they occur. Means the order in which you are going to take the prime factors, it doesn't matter, but in the end you are going to get the same prime factors. Only thing is that given composite number we are going to divide only by prime numbers. So this is the statement for fundamental theorem of arithmetic. Every composite number can be expressed as a product of its prime factors apart from the order in which they occur. Means order is not important, but then too we are going to follow the order for sake of easiness. We'll start from the smallest prime number 2, then we'll go for 3, then 5, then 7, 11. Like this we are going to divide given composite number only by prime numbers, okay, to get the prime factorization quickly. Getting it? Let us discuss some more examples of this. 180 if you follow this method or factor tree to do the prime factorization of 180, we will get it as 2 into 2 into 3 into 3 into 5. In the power form, we can write this as 2 square into 3 square into 5 raised to 1. Next one, suppose we take 5313. This can be written as 3 into 7 into 11 into 13. Next one, if we take 10,626, again by using prime factorization, this can be written as follows. You can see it, you can try for these examples. So this is all about fundamental theorem of arithmetic. It's very simple, and we can say that fundamental theorem of arithmetic is nothing but it deals with prime factorization of the given composite number, and we can say that every composite number can be written as a multiplication of its prime factors. Now we are going to start with the questions based on the concept of fundamental theorem of arithmetic, that is nothing but prime factorization. Let us start with the first question. The first question, express each of the following numbers as a product of its prime factors, which you can do very easily. You can go with ladder method or factor tree method to do the prime factorization, and in the end you can write that prime factorization in the as a multiplication of the prime factors. Let us see the first one, 140. 140 can be written as 140, first of all, it is divisible by 2, so we can write it as 2 into 70. 70 is once again divisible by 2, so can be written as 2 into 35. Now 35 is not divisible by 2, so we'll go for 3. It is not divisible by 3 also, so we'll go for 5. So 35 can be written as 5 into 7. Now 5 and 7, both the numbers are prime, so we will stop our factorization here, and this 140 can be written as 2 into 2 into 5 into 7, that is 2 square into 5 into 7. Next one, if you take 156, first of all it is divisible by 2, then again 2, then it is divisible by 3, then 13. Okay, you can see the sequence, I don't need to explain it much. 156, first of all, clearly it is divisible by 2, so we'll get quotient as 78. Now 78 is divisible by once again by 2, so we'll divide by 2, we'll get quotient as 39. 39 is divisible by 3, so we'll get quotient as 13. 3 and 13, both the numbers are prime, so we'll stop our factorization here. So 156 can be written as 2 into 2 into 3 into 13, that is nothing but 2 square into 3 raised to 1 into 13 raised to 1. Next, 3825, this can be written as first of all, actually you should start with 2, but it is not divisible by 2, then go for 3, then once again 3, then 5, then 5, in the end you get 17. Doesn't matter in which order you are going to do it, but for sake of easiness I told you to follow the order, so we'll get its factorization like this. So prime factors of 3825 are it can be written as 3 into 3 into 5 into 5 into 17. Next one is 5005. It is not divisible by 2, not divisible by 3, so we'll directly go for 5. It can be written as 5 into 1001. So now it is not divisible by 5, so we'll go for the next prime number, which is 7. So if we divide this by 7, we'll get 7 into 143. Now this 143 is not again divisible by 7, so we'll go for the next prime number, 11. It is divisible by 11. It can be written as 11 into 13. And 11 and 13, both the numbers are prime, so we'll stop our factorization here. So in the end, we can write the answers like this. 140 can be written like this, 2 into 2 into 5 into 7. 156 can be written like this, 3825, and 5005 like this. So whenever you'll be asked such kind of questions, first of all you'll be doing its factorization by using ladder method or factor tree method. It doesn't matter which method you are going to use, and then you are going to write those factors as multiplication, and then the given number will be written as product of its prime factors. If you want, you can write this as in the power form also. This is now let us see some more applications of fundamental theorem of arithmetic. Actually, this fundamental theorem of arithmetic or prime factorization can be also used to find HCF and LCM of the given numbers. Doesn't matter whether there are two numbers, three numbers, or more numbers. So first application of fundamental theorem of arithmetic, which we are going to study now, is to find out HCF and LCM of the given positive integers. Now, to find out HCF and LCM of the given positive integers, definitely we have two different methods. First of all, the first method, which we have studied already in the lower classes, that is, suppose we have given two positive integers, simply express those positive integers as product of its prime factors, and to find out HCF we will just take pairs of the common factors, and LCM will be HCF into uncommon factors. But this year we are going to study another method of finding HCF and LCM by using prime factorization, that is nothing but called as power method. So let us see how exactly are we going to find out the HCF and LCM by using these methods. First of all, let us discuss how we will find out HCF of given numbers by using prime factorization. So to find out HCF, we will use this. HCF of composite numbers when written as prime factorization is given by product of the common prime factors with the lowest powers. Okay, we will discuss this in details when we are going to study the examples based on this immediately after this note. And to find out LCM, that is lowest common multiple of composite numbers when written in the prime factorization, is given by product of the common prime factors with the highest powers. Now these two things, two definitions, I will explain it properly when we will take a particular example. So for that, let us take one example. Suppose we are going to find out HCF and LCM of 6 and 20. So first of all, what we will do, we will write 6 as the product of its prime factors, as well as 20 also as the product of its prime factors. Then we will write the prime factorization in the power form. Getting it? So let us see. 6 can be written as 2 into 3, and 20 can be written as 2 into 2 into 5. Okay, so now what are we going to do here? See, in the prime factorization of 6, 5 is not there, but then too we will involve 5. How we are going to involve 5? By keeping the power of 5 as 0. 5 raised to 0 means 1 only, so it is not going to change the value of our given number. Similarly, in the prime factorization of 20, 3 is not there, so we are going to introduce 3 also here by giving its power as 0. So see, 6 is actually written as 2 into 3, which can be written as 2 raised to 1 into 3 raised to 1. 5 is not there, but 5 is present in the prime factorization of the other number. That's why we are taking here 5, and we will write power of 5 as 0. Getting it? Next, 20 is the another number. For 20, we can write it in the power form like 2 raised to 2, 2 square, multiplied by 3 is not there in the prime factorization of 20, but it is in the prime factorization of 6. So we'll take that 3 here with power 0. 3 raised to 0 means 1 only, and 5 is has appeared once, so 5 raised to 1. So in this way, both the numbers 6 and 20 are written as a product of its prime factors, and the numbers which we were not present, we have written as the by taking power as 0. Getting it? So here we have made all the factors as common. Now what exactly above definitions are telling us? Suppose first of all we are going to find out HCF of 6 and 20. So according to above definition, HCF of 6 and 20 is nothing but multiplication of common prime factors with the lowest powers. Now here we have made all the factors common. 2, 3, 5 we have made available in both the prime factorizations. Okay, so what we have to do in these prime factorization, from these prime factorizations, we are going to do the multiplication of the prime factors with the lowest powers. So to find out HCF of 6 and 20, what we'll do? See, 2 is the common factor. In the prime factorization of 6, we have 2 raised to 1, and for 20 it is 2 raised to 2. What we will do? Out of these two common factors, we will take the common factor with lowest power for HCF. Okay, so that is nothing but 2 raised to 1. So we'll take 2 raised to 1. Now Second factor is 3. In prime factorization of 6, it is 3 raised to 1, but in 20 it is 3 raised to 0. So lowest power is 0, so we'll take 3 raised to 0. So for HCF, we are always going to take lowest powers of all the common factors. Similarly for 5 also. In 6 it is 5 raised to 0, in 20 it is 5 raised to 1. Lowest power is 5 raised to 0, so we are going to take that. The lowest power is 0, so we'll take 5 raised to 0. Getting it? So to find out HCF of the given numbers, we have taken multiplication of the common prime factors with lowest powers. Getting it? So we have got 2 raised to 1 into 3 raised to 0 into 5 raised to 0. 2 raised to 1 is nothing but 2 only. 3 raised to 0 is 1. 5 raised to 0 is 1. Doing this multiplication, we will get the HCF of the given numbers as 2. Getting it? Similarly, whenever we are going to find out LCM of the same numbers, at that time we are again going to use the same technique, but instead of taking lowest powers for LCM of the given two numbers, we will take highest powers. So what will happen if we take highest powers to find out LCM of these two? So 2 raised to 2 will be taken, because 2 raised to 1 and 2 raised to 2, these are the two common factors. 2 raised to 2 is the number with the highest power. Then 3 raised to 0, 3 raised to 1, these two are the numbers. 3 raised to 1 is the number with the highest power. 5 raised to 0 and 5 raised to 1. 5 raised to 1 is the number with the highest power. So we have taken all the common prime factors with highest powers to find out LCM of the given numbers. Now let us solve them. 2 raised to 2 is 4, 3 raised to 1 is 3, 5 raised to 1 is 5. Doing the multiplication of this, 4 into 3 into 5 will get as 60, which is LCM of the given numbers. Okay, so this is the power method of finding the LCM and HCF of given two numbers. It can be used for any numbers. Suppose we are given 3 numbers, 4 numbers, 5 numbers. Okay, this will be easier method to find out their HCF and LCM. The same question can be solved with another method, our orthodox method, to find out HCF and LCM. Let us see that also. It doesn't matter if you solve with this one, but it will be always better if you go with the power method if you have given more than 2 numbers. See, 6 can be written as 2 into 3, 20 can be written as 2 into 2 into 5. To find out HCF of these two numbers, we will just take the numbers which are common in both the factorization. Only 2 is common in both the prime factorizations, so 2 is written there. So 2 is nothing but HCF of the given two numbers. For LCM, what we do HCF, that is common factors, multiplied by uncommon factors. So whatever common factors are there, for one pair we write one number, or simply you see it as HCF into uncommon factors. That will be better. So HCF is 2, which is written there, and multiplied by uncommon factors, 2 into 3 into 5. So multiplication of all this will give us 60. So this is another method of finding HCF and LCM. I think that it will be always better for you if you go with this one to find out LCM and HCF of two numbers. Or if you have understood the power method, you can go with that also. But actually, power method will be useful to you whenever you are going to find out HCF and LCM of 3 or more numbers. It will be always beneficial to you to find out LCM and HCF. Okay, so mostly we are going to focus on power method because you are very much familiar with this orthodox method of finding LCM and HCF. The second method, which we have just seen. Let us see the next part. Note: in above example, what do we see? What we are going to do? We are going to study one relation between HCF, LCM and the given numbers. So we simply will take multiplication of HCF of two numbers and LCM of two numbers. HCF is 2 and LCM is 60. So 2 into 60 will get 120. Now we will take product of the given numbers. Product of the given numbers are 6 and 20. So their multiplication will give us also 120. So from 1 and 2, what do we see? HCF of 6 and 20 into LCM of 6 into 20 is equal to product of the numbers 6 and 20. So from this we can write a note that for any two positive integers a and b, HCF of a and b into LCM of a and b is equal to a into b. That is nothing but product of the numbers. So if we have given two positive integers, multiplication of their HCF and LCM is always equal to product of those numbers. Remember this note. We are going to see some more examples based on this note. And one more thing you can see here is, see, in above example, the value of HCF is 2 and the value of LCM is 60. Whenever you are going to find out HCF and LCM of the given numbers, you will always find that LCM is a multiple of HCF, or in other words we can say that HCF is always a divisor of LCM or a factor of LCM. Okay, so here clearly we can see that 2 divides 60, 2 into 30 is equal to 60. So whenever we are going to put HCF and LCM, you always have to remember that HCF is always a divisor of LCM of the given. Now let us discuss a question based on this concept. That is, we are going to find out HCF and LCM of the given numbers, and we will also verify the relationship between HCF and LCM and product of the numbers. So question is, find the HCF and LCM of 2100 and 2640 and verify the relation LCM into HCF is equal to the product of the numbers. So let us solve this by using power method first. I will always prefer this method rather than going with our orthodox method. So what we will do, first of all, we will do the prime factorization of 2100, which can be written as 2 into 2 into 3 into 5 into 5 into 7. This you can do easily. Then we will do prime factorization of 2640, which is 2 into 2 into 2 into 2. 2 will appear 4 times, into 3 into 5 into 11. Now see, so what are we going to do? First of all, common factors 2, 3, 5 and the uncommon factors. Now 7 is present in the factorization of 2100, but it is not present in the factorization of 2640. Similarly, 11 is present in the prime factorization of 2640, but it is not present in the prime factorization of 2100. So we are going to adjust them by taking the powers 0 accordingly. See, 2100 can be written in the power form as prime factorization, like 2 raised to 2 into 3 raised to 1 into 5 square into 7 raised to 1, because 7 has appeared here once, and 11 is not present. That's why 11 raised to 0 means 11 has appeared here 0 times. So 11 raised to 0. Why are we taking 11 here? Because 11 is present in the prime factorization of the other number. That's why. Similarly, 2640 can be written as a product of its prime factors in the power form, like 2 raised to 4, because 2 has repeated 4 times, 3 raised to 1, 3 has come only once, into 5 raised to 1, 5 has come once. 7 is not present in the prime factorization of 2640, but it is present in the factorization of 2100. So we'll write here 7 raised to 0, means 7 has appeared 0 times in this factorization, multiplied by 11 raised to 1, means 11 has come once in this prime factorization. Now as soon as we will write it like this, it will become very easy for us to find out HCF and LCM of the given two numbers. So let us first of all go for HCF of 2100 and 2640. So it will be written as multiplication of the common prime factors with the lowest powers. So all the factors we have made now common, which were not available, we have made their powers, taken their powers as 0 and written it. So all the factors are common now. What are we going to do? Simply we are going to take the common prime factors with lowest powers. So HCF of these numbers can be written as, see, 2 raised to 2 is taken. We have 2 raised to 2 and 2 raised to 4. 2 raised to 2 is the number with the lowest power. Here we have 3 raised to 1, 3 raised to 1. Both the powers are same. So we'll take 3 raised to 1 only. Nothing, no one is greater and no one is smaller. Both are equal. Okay, so we'll take 3 raised to 1 only. 5 square and 5 raised to 1. 5 raised to 1 is the number with the lowest power. So for HCF, we are taking lowest powers. 7 raised to 0, because it is the number with the lowest power. 7 raised to 1 and 7 raised to 0 we have. And similarly, multiplied by 11 raised to 0. And multiplication of all these numbers, 2 raised to 2 is 4, 3 raised to 1 is 3, 5 raised to 1 is 5, 7 raised to 0 is 1, 11 raised to 0 is 1. And again multiplying all these numbers, we'll get 60, which is HCF of the given two numbers. Getting it? So this is the way of finding HCF of the given numbers. We'll take the lowest powers of all the common factors and we'll do their multiplication. If some factors are not available, we'll adjust those factors by taking power as 0. Similarly for LCM, instead of taking lowest powers, we will take highest powers of the common factors. So LCM of the same numbers will be, now we have taken 2 raised to 4 because this is the number with highest power. 3 raised to 1, in both the numbers there is power 1 only, up 3, so we have taken 3 raised to 1. 5 raised to 2 is taken because it is the number with the highest power. 7 raised to 1, number with highest power. 11 raised to 1, number with highest power. Then we have written the answers of these numbers. 2 raised to 4 is 16, 3 raised to 1 is 3, 5 square is 25, 7 raised to 1 is 7, and 11 raised to 1 is 11. Multiplying all these numbers, we'll get answer as 92,400, which is LCM of the 2100 and 2640. Getting it? So this is the way of finding HCF and LCM of the given numbers by using power method. Actually, this is very easy. Whenever we are going to do it with power method, whenever we are going to do it for 3 numbers, it will be done in the similar way. And simple thing which we have to remember is we have to write the given numbers as the product of the prime factors in the power form, all the numbers whatever are given. For HCF, we are going to take the numbers with the lowest powers and their multiplication, and for LCM we are going to take the numbers with the highest powers and their multiplication. Okay, so this is the thing. Now second method, which is orthodox method to find out HCF and LCM of the given numbers. Let us see that method also. So in this method, first of all we'll write the factorization of 2100, that is 2 into 2 into 3 into 5 into 5 into 7. Then we'll write the factorization of 2640, which is 2 into 2 into 2 into 2 into 3 into 5 into 11. So by our regular method, orthodox method, to find out HCF of these numbers, we take the numbers which are common in both the factorizations. 2 is the first common number, then another 2. 2 has come twice, so for one pair we write one number. So second pair of 2 we have written another 2. 3 is also common in both, so for that pair we have written 1 3. 5 is also common in both, so for that pair we have written 1 5. Only we take the common numbers and their multiplication, and this multiplication gives us 60, which is HCF of the given numbers. For LCM, how do we write LCM? HCF multiplied by uncommon factors. So HCF here is 60, which we already have calculated in the above step, and multiplied by uncommon factors which are left. So 2 2s are left, 1 5 is left, 1 7 is left, and 1 11 is left. So all these multiplications will give us 92,400. Getting it? So this is our regular method which we are using previously to find out LCM. You can do with this method also, but both the methods you should do. It's not like either you should do this or that. You should be good in both the methods to find out HCF and LCM. Power method will be definitely useful for us if we have bigger numbers or numbers more than 3. Suppose we have given 3 or more numbers, power method will be useful to us. Now remaining part of this question, that is to verify the relation LCM into HCF is equal to product of numbers. To verify this, first of all, let us find out the answer of multiplication of HCF and LCM of 2100 and 2600. HCF is 60, LCM is 92,400. This multiplication gives us 55,44,554,000. Then let us multiply the given numbers. Product of the given numbers, that is 2100 into 2640, which will also give us 5544,000. 55,44,000. So from 1 and 2 we can clearly see that HCF of 2100 and 2640 into LCM of 2100 and 2640 is equal to 2100 into 2640. That is, product of numbers is equal to LCM and HCF, hence verified. So whenever they'll be asking you to verify, first of all you should do the multiplication of HCF and LCM, call it as number 1. Then you do the product of the given numbers, multiplication of the given numbers, see what is the answer, call that as number 2, and from 1 and 2 you can write that the relation is verified, that is HCF and into LCM of the given numbers is equal to product of the numbers. And this relation should be verified always. If your values are not coming equal, means you have committed error somewhere. Getting it? These values should always come equal, because we have written this as a note. It is a remark. Okay, it is the identity which cannot be, it cannot have any absurd. Getting it? So it should always hold true. Let us start with the second question. Now this question is based on the relation, that is HCF into LCM is equal to product of numbers. Let us start with our second question. We have given that HCF of 96 and 404 is equal to 4, and they have asked us to find out LCM of the same numbers. Getting it? So to do this, first of all, we know that we have given both the numbers. The given numbers are 96 and 404, and we have given the value of their HCF also. We are supposed to find out LCM of the given two numbers. So let us see the answer. The answer, we are going to start by using our remark, the relation between HCF, LCM and product of the numbers. So we know the relation that HCF into LCM is equal to product of numbers. Let us put the values here. So we'll get HCF of 96 and 404 into LCM of 96 into 404 is equal to product of numbers, that is 96 into 404. These are the numbers. Let us put the values. So we have given the value of HCF as 4. So 4 multiplied by LCM of the given numbers is equal to 96 into 404. I will recommend that you should not do the multiplication on the RHS. It will simply lead you to some big answer. Don't do that multiplication. Keep it as it is, because LCM or HCF, whatever is there on the left handed side, is definitely going to divide both the numbers. So next step, we are going to transpose that 4 on the RHS. 4 is multiplied to the LCM. So on the other hand, it is going to divide RHS. So we will get LCM of the given numbers is equal to 96 into 404, which is our RHS, divided by 4. 4 was multiplied on left. Here it is divided. So that 4 is dividing 404 as well as 96. You can divide one of the numbers. Let us divide 4 to 404. So we will get LCM of the given numbers is equal to 96 multiplied by 101. So 404 is divided by 4. We have got 101. So LCM of the given numbers we have got as 9696. So in this way you can solve the problems. Sometimes they may give you LCM and will ask you to find out HCF. Sometimes they will give you the value of HCF, LCM and one of the numbers, and they will ask you to find out other number. Getting it? So by using this relation, simply we can solve this question. Getting it? I have given some more questions of this type of homework. Let us see the next question. It is a 1 mark question. Question is, can HCF of two numbers be 12 and their LCM be 66? Okay, it is a 1 mark question. The question is very simple. To solve this question, we should know one fact. What is the fact? We have already seen it, that HCF is always a divisor of the LCM of the given two numbers. Getting it? So let us start with that note. Let us start with the answer. We know that HCF is always a divisor of LCM. Okay, so clearly here we can see that 66 is not a multiple of 12, or 12 is not a divisor of 66. 12 doesn't divide 66. So we can clearly say that two numbers cannot have 66 as LCM and 12 as their HCF. This is the end of the answer. We just require to write the note that HCF is always a divisor of LCM, or you can write LCM is a multiple of HCF. Okay, so in this question clearly we see that it is not happening. That's why two numbers cannot have 66 as LCM and 12 as their HCF. Now let us start with the next question. Question number 4. We are going to see how are we going to find out HCF and LCM of three positive integers. Question is to find out HCF and LCM of 6, 72 and 120. First of all, let us write this as prime factorization, product of prime factorization, prime factors. So first of all, let us write it for 6. 6 can be written as 2 into 3. 72 can be written as 2 into 2 into 2 into 3 into 3. And 120 can be written as 2 into 2 into 2 into 3 into 5. So we can see that 5 is not present in the prime factorizations of 6 and 72. We will make it present there in the power form by taking power as 0. So once again, 6 can be written as 2 raised to 1 2 has come once, 3 has come once, and 5 is not there, so 5 raised to 0. 72 can be written as 2 cube into 3 square into 5 raised to 0 because 5 is not there, and 120 can be written as 2 cube into 3 raised to 1 into 5 raised to 1. See, I have already told you, whenever we are going to find out HCF and LCM of 3 or more positive integers, we always have to prefer the power method than our orthodox method. Getting it? So now to find out HCF of the given numbers, what we will do, we will take the product of common prime factors with the lowest powers. So we have 2 raised to 1, 2 raised to 3 and 2 raised to 3. We have 2 raised to 1 is the number with the lowest power. In second factor, 3 raised to 1 is the number with the lowest power, and in third one, 5 raised to 0 is the number with the lowest power. Again, solving this, 2 raised to 1 is 2 into 3 raised to 1 is 3 and 5 raised to 0 is 1. Their multiplication is 6, which is nothing but HCF of the given numbers. Now to find out their LCM, what we will do? Simply we will take the multiplication of the common factors with the highest powers. So rather than taking lowest powers, we are going to take highest powers now. So that will be 2 raised to 3 into 3 square into 5 raised to 1, which will be 8 into 9 into 5, which is nothing but 360, which is LCM of the given 3 numbers. So in this way we can find out HCF and LCM of 3 numbers. With this, we are going to see one more note. Now the note is like this. We have seen that if we find HCF and LCM of 2 positive integers, the product of HCF and LCM is always equal to product of the numbers. But this is not applicable for the 3 positive integers. See, so what are we going to write? In above question, first of all, we can clearly see the multiplication of HCF and LCM of the given 3 numbers is HCF is 6, LCM is 360, which will give us 2160, and product of the numbers, that is 6 into 72 into 120. This is the product of 3 numbers, which is giving us 51,840. So from these 2 statements, we can clearly say that for 3 positive integers, HCF into LCM is not equal to product of 3 numbers. Similarly for 4 numbers and more numbers also. But there is one exception for this also. This can hold true if and only if HCF of the given 3 numbers is 1. So we can say that for 3 positive integers, HCF into LCM is equal to product of the given 3 numbers if and only if, that is nothing but IFF I have written, HCF of the given 3 positive integers is 1. And next one, to find out HCF and LCM of 3 or more positive integers, we should always use power method in the prime factorization. That will be always better rather than using our orthodox method to find out HCF and LCM. Let us start with the next question. The question is, check whether 12 raised to n can end with digit 0 for some natural number n. Now to solve such kind of questions, you should know one thing. Which numbers are ending with digit 0? The numbers like 10, 20, 30, 40, 60, 70. Means in short, we can say that all the multiples of 10 are ending with digit 0. So if you take any number which ends with digit 0, 10 is the factor of that number and 10 is a composite number. And again, if you do the factorization of 10, we will get 2 into 5. Getting it? Now, if a number is ending with digit 0, for example, if you take 70, so 70 is nothing but 7 into 10. Getting it? Means 110 is always there. That's why we can say that 70 is ending with digit 0, and 10 contains 2 prime factors, that is 2 as well as 5. So in short, we can say that a number can end with digit 0 if and only if it contains 2 as well as 5 in its prime factorization. If one of the prime factors from 2 and 5 is absent in it, that number is definitely not going to end with digit 0. So let us see the answer of this one. 12 can be written as 2 into 2 into 3, but we have given number as 12 raised to n. So let us take nth power on both the sides. By taking nth power, we'll get 12 raised to n is equal to 2 into 2 into 3 whole raised to n. So what do we see here? We can write the note: a number ends with digit 0 if and only if it contains 2 as well as 5 in its prime factorization. Both the numbers should be present in the prime factorization, 2 as well as 5. But we can see that in the prime factorization of 12 raised to n, 2 is present but 5 is not present there. So next sentence we can write: 12 raised to n contains prime factor only 2. As it does not contain prime factor 5, we can say that 12 raised to n does not end with digit 0, or it cannot end with digit 0 for some natural number n. Getting it? So it is very simple to solve. Suppose they are asking you to check whether some number is ending with digit 0 or not. Simply you will do its prime factorization, and if that prime factorization is containing prime factors 2 as well as 5, then only given number can end with digit 0, or else it cannot end with digit 0. Let us write a note for this. First note: a number ends with digit 0 if and only if it contains 2 as well as 5 in its prime factorization. Sometimes they may ask you to check whether a number is ending with digit 5 or not. So when a number will end with digit 5, if it contains at least one 5, doesn't matter what are the other numbers, but it should contain at least one 5 in its prime factorization and not a 2. It should not contain 2. Getting it? So a number will end with digit 5 if and only if it contains 5 in its prime factorization. Doesn't matter what are the other prime factors, but it is very important that 2 should not be present in the prime factorization. At least, see, we have written the note: a number ends with digit 5 if it contains at least one 5 in its prime factorization. In this, I would like to add that 2 should not be present there. If 2 is present there, then what will happen? Then that number will end with digit 0. It will never end with digit 5. Getting it? So if a number has to be end with digit 5, then it should contain at least one 5 and it should not contain 2 in it. Now let us start with the last question based on fundamental theorem of arithmetic. This question is also very simple. The question is: explain why 3 into 5 into 7 into 11 plus 10 is a composite number. Now, what is a composite number? We already have studied the definition of a composite number in the beginning of this class. The composite number is nothing but a number which has more than 2 factors. Okay, a number has more than 2 factors, means 3 or more than 3 factors. Means if we can write the given number as a product of 2 different numbers other than 1, that number is nothing but a composite number. Suppose, for example, if we have given 10, now 10 can be written as 2 into 5, which does not involve 1 in it. We can say that 10 is a composite number. So similarly, same logic we are going to apply here. This expression we are going to write as a product of 2 different positive integers other than 1. So let us start with the answer of this one. See, we have given the expression 3 into 5 into 7 into 11 plus 10. This can be written as, we can see 3 into 5 into 7 into 11. This will be considered as one term only, and 10 is the second term. We know in mathematics terms are separated by plus or minus sign only. So from both these terms, 5 can be taken common. Okay, 5 can be taken common from the first term, that is 3 into 5 into 7 into 11, and from 10 also we can take 5 common. So we have taken out 5 multiplied by inside the bracket 3 into 1 into 7 into 11 plus 2 will remain in place of 10. So again, next step we can write, this can be written as 5 multiplied by multiplication of 3 into 1 into 7 into 11 will give us 231 plus 2. Next step we can write, this is nothing but 5 into 233. Now don't do this multiplication. Now this much is sufficient for us to say that given number is composite. Why? Because as given expression is expressed as a product of two different positive integers other than 1, it is a composite number. This is the required answer. You are supposed to write it in this way. Now homework questions. As usual, you are going to solve all the questions for the homework. I've given at least one question of every type, some where you will find that there are more questions of the same type. The first question is very simple: express given numbers as a product of the prime factors. The second question: find HCF and LCM of the given pair of integers, and then verify the relation between them, that is LCM into HCF is equal to product of the numbers. The third one, you have to find out HCF and LCM of the three positive integers by using prime factorization. Solve this question by using power method. I have already suggested. The fourth question is very simple. You can see it. Already we have solved a question like this. Fifth question can be solved by using relation. HCF into LCM is equal to product of numbers. Sixth question, seventh question, and eighth question, we have already seen how to solve such kind of questions, whether a number can end with digit 0 or 5. They have asked for 0. If number will end with 0 if the given number contains 2 and 5 in its prime factorization, and a number ends with 5 if it contains at least 1 5 in its prime factorization but not 2. Then question number 9. The question number 9 is explain why the following expressions are the composite numbers. I have given 3 questions in it. You just have to write the given expressions as the product of two positive integers. That is sufficient to say that they are composite. So we will express given expressions as a product of two positive integers other than 1. 1 should not be there. You cannot write 1 into something and can say that this number is composite. Getting it? So this is your homework. Complete the homework. Enjoy this. Next lecture will start with the third concept of this chapter. All the best. Thank you.